Fantastic. All right, it is 4 p.m. on a cloudy and cold day in April, which is strange. So I'm in a sweatshirt because it's cold outside. We are talking about our exam 4 review. So a reminder that our exam is on Saturday, starts at 10 a.m. So as usual, try to be there before 10 a.m. Be early. Because the last time I looked at the weather, which granted it keeps changing, but it's supposed to rain on Saturday, so do try to be early to avoid traffic. This exam is covering this content, so chapter 15. This is thermodynamics. So this is the part where we talk about thermodynamics. I'll get that in there. Misspellings. So this is the part where we were talking about things like Gibbs free energy. And particularly relating things like the standard Gibbs free energy, relating it to equilibrium. So both dealing with Gibbs free energy, also dealing with whether something's spontaneous or not, and talking about its relationship to both enthalpy and entropy. So it's a little bit of chapter 15. Chapter 16.4, that actually is the part that relates it to equilibrium because it's in the equilibrium chapter. Chapter 19 is the part that's all about electrochemistry. So this is the part where we were starting off with things like redox reactions, and trying to deal with in a simplistic way. Let me grab something to start off with. This was the simple one. Something like iron and cobalt goes to iron 2+ plus cobalt 2+. And we could talk about things like oxidizing agents and reducing agents and the species oxidized and the species reduced, as well as some calculations involved in there. So that is just kind of a really broad overview of what's going on in these chapters. A couple of things that is also here, but I'll mention it. The 16.4 excludes free energy diagrams. So there was a time where we did teach these. So depending on if you're looking at any sort of previous material, I frankly used to refer to these as the Nike swoosh graphs because the graph actually looks like that. What it looks like, but this is not this year. Not 2023. We're not doing it. So that stuff is not on the exam at all. Similarly, we are just getting. We're not teaching concentration cells this year. A concentration cell is just where it's actually the exact same species. So, for example, in this reaction I have down below, if it was nothing but cobalt, if it was just cobalt and nothing but cobalt, that's a concentration cell. It's a really specific example that we're not including mostly for time, and they're not as common. So if you ever needed that in real life, you could figure it out pretty readily with the information you already have. The other things on here, however, electrolysis in water and quantitative applications of electrolysis, these are both things that we're going to cover and will be on the final. So we are going to cover these, but we're just going to cover them after exam 4. So while there are some topics that we have covered in previous semesters, the free energy diagram, the Nike swoosh diagram, and concentration cells that we're just not covering this semester, it won't be on the final exam. The other 2 topics that I've highlighted in pink, the electrolysis in water, as well as the quantitative applications of electrolysis, we will put on the final exam, but we're going to cover them after exam 3. So if you do come across any questions about those are kind of nice to like put a little asterisk by, put a little star by it, and do it not next week, in 2 weeks. So still, they're good questions to do, but not for exam 4. They're good for the final. So hopefully that gets us a little bit of information to get started. The other thing I'm actually going to do, and I know people will ask questions about this, so I never do this, but I have to admit that I actually made myself an equation sheet for this exam review. So we're just going to go ahead and talk about that. Now, as usual, this is not a promise that these are all of the equations, and I'll do a little bit of a hand wave to demonstrate what I mean by this is not all of the equations, but this is a lot of them, or at least the ones I'm coming prepared to talk about. So one of them is this beautiful one. Oh, good, make this a standard one. It's H minus T delta S. I'll put those in there. One of the ones that I usually don't write out all of them is the one where if I'm looking for delta G standard of a reaction, I can get that by looking at, I typically just write this as products minus reactants. We can certainly do one of those. That's when you pull the information from the table, pull values from table using stoichiometry. So whatever coefficients are from the reaction, we would use those in there. That, by the way, also does go for delta H of a reaction is calculated the same way, along with delta S, your entropy of the reaction, same way. That's what I meant by I'm not going to quite do all of the equations, but we'll do a couple of them before I forget. Speaking of that, standard Gibbs free energy is also equal to RT ln K, where R is the gas constant, but it's the weird gas constant. So we are in thermodynamics, which means we need joules, we need energy. Capital T is still the temperature in Kelvin. I say still because I don't know if y'all have noticed, but most of the letters that we wind up using in chemistry, they don't always mean the same thing depending on their context, or even R. R is actually always the gas constant, but the units change depending on what we're doing, and when the units change, the value changes. But capital T in chemistry, actually always the temperature in Kelvin. We did, however, use a lowercase t. There's a negative sign there. Yes, there is. And if I wanted to talk about spontaneity instead of delta G standard, I'd use this guy. And if I'm talking about does something actually go to products or to reactants, I'd need Q instead of K. Then, oh, I didn't, sorry. I'm looking at my own notes and realizing that all I wrote down was that. Great job, Dr. Taylor. Did you want to write down an equation that goes with that? Apparently not. There's two different ways to calculate E-cell standard. I'm going to actually write down what's in ALEX, which is you pull this, I'm not done yet, the reduction reaction minus the oxidation reaction, and this is for pulling off the table. We can talk more about that one as well. Speaking of things with to do with E-cell, we can also relate that to Gibbs free energy, negative NF. And this one's also kind of an odd one because essentially we can talk about spontaneity as well, or we can talk about the standard version. So this is one of those where either both things are standard or both things are not standard. They both relate to each other. Here N is moles of, actually no, not moles of electrons. That's a misnomer. This is the number of electrons transferred. And E-cells, oh, E-cell standard, we'll talk about that later, sorry. F is Faraday's constant. When you see Faraday's constant, depending on the textbook, this is either a capital F, sometimes it's a fancy capital F. Also, sometimes if I'm feeling fancy, I will sometimes write it in cursive. Ooh, apparently not feeling fancy. Probably could figure that out by the sweatshirt. But Faraday's constant, which means it's on the back page of the exam. On back page of exam. And if we actually need it, I'll pull the number. Those are not the only equations. 2 more. Oh, 3 more. Because. Da, 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 da. I haven't gotten to these yet in class. Positive. Yes, positive. Sorry, this is the reason, by the way, that I did this, is because I basically, before I started, went double check to make sure I had all my positives and negatives correct on here, because as we go along, those can get a little bit tricky. And then basically there's a version of this where, since R is a gas constant, F is a constant, as long as we say that we are at 298 Kelvin, which is typically used for thermodynamics, we can actually rephrase this 0.592 divided by n times the log of K. A lot of the instructors like this one. I have slowly but surely come around to it. I usually actually use the top one that uses the natural log instead, but I sometimes do use this one. So I'm going to be trying to use the log of K because that's what most of my colleagues use. Whenever I check the exam, I always check using, personally, I check using both of these to make sure that the numbers are close to each other. And then if we wanted E-cell, not standard, we could do that too. Here I did actually just grab 0.592 without the different temperature version times log of Q. Okay. So this is not all of the equations, by the way, not actually all of the equations, but it's a lot of them. And as we go along, maybe we'll find the ones I forgot. Also, I'm gonna put my phone on silent while I'm thinking about this. So I did a giant equation list for 2 reasons. One, because that is something that I did to prepare for the exam review, and I expected somebody to ask me. If you did want to ask the famous question of how many equations are there on the exam, I still have to go with I don't know, because I never know if you count these 2 as 1 equation or 2 equations, because this top one that has the RT and F in it is the same equation as the one below it. It's just the top one is for use at any temperature, and the bottom one that's partially in red is for use at 25 degrees Celsius. So I'm never entirely certain if you want to count this as 2 different equations or the same equation. So that is a thing that I don't know. Similarly, this one on the bottom, we could actually do a version of this that's valid at any temperature, and then it should actually look a lot like the top one that we can't actually see now, but RT divided by NF times the log of Q. The other thing is that the other reason I actually did want to do this kind of equation system at the beginning is what you might notice is that there's a lot of similarities between these equations because a lot of them go together. So really part of the reason I wanted to do this is because when you start to look at them, you've got something that relates our electrochemistry standard E-cell term to our equilibrium constant, and we have an equation that relates our delta G standard, our standard Gibbs free energy, to equilibrium. We have something that relates when we're not necessarily at standard states. And if we're not at standard state, then we're dealing with Q instead of equilibrium. So that's what this equation gives us, is it talks about, well, what happens if we're not at equilibrium, if we're not at standard conditions, then what? That's what this equation in blue is for. And similarly, we have equations to say, hey, what if we're not at standard conditions? What if we're not at equilibrium, but we're dealing with electrochemistry? What happens then? So there's a lot of overlap in these systems of equations to talk about both equilibrium and Q, Gibbs free energy, and E cell. They actually all go together really well. I didn't define what any of those were. So let's go ahead and see where we are with questions. How are we doing? How's the chat doing?
All right, so we got a few questions in so far. Looks like 5 or so. Okay, so the first one is, will we also need to practice the last bit of solubility? Dr. Dykman sent out an announcement that has been moved to this exam.
Okay.
Next is, what would be an example of a conceptual and calculation question regarding electrolytic cell slash galvanic cell slash voltaic cell?
Okay.
All right. Next
Hold
is
almost there.
Okay.
There's a lot of good terms in that one. So I actually want all of those pieces. Okay, now what next?
All right. Next is, can you go over standard reduction potentials?
Okay.
Next is, what are the units we should remember for delta G, entropy, enthalpy, etc.?
Okay.
And the last one at the moment is the gas constant also on our cheat sheet, or will we need to memorize it?
Cool.
Sweet. That's all for now.
Can do. Great. Okay. Let's start at the top because so let me see if I can blow this up. Otherwise I'll hit the edit. No, there we go. Let me make it bigger. Okay. So a note about the solubility content. It says there are 2 topics that were not tested on exam 3 due to length of the exam, and they're listed: the common ion effect on solubility and the comparison of QSP and KSP. Then it says underneath that these topics will be tested on the final exam. That does mean your 2-hour and 45-minute final, that's on Tuesday, May 9th. So that does not mean exam 4, that actually does mean the final. I definitely understand that it's always better to ask, but it is on the final. So a quick reminder, or perhaps being told for the first time, I'm not sure. I gotta work on that. Fine, it's my problem, not your problem. So that's on the final, which is Tuesday, May 9th at 8 p.m. a.m. Do I have the thing I need to make my note? No, I don't. I gotta remember. Hold on. There's something that I have just remembered, and if I don't make myself a note, I will be mad because they're probably going to ask me about it tomorrow. My colleagues, by the way, in chemistry, not my class. Final exam, ARC student, because I'm in charge of that. All right, I made myself a little note. I'll put it over there. So, excellent question. You do need that for the final, but you don't need that for exam 4. Excellent question. Then actually I'm gonna tackle so I did that one. Then I'm gonna go ahead and tackle the gas constant. This actually is still on your potentially useful information. I actually think if you looked at one of your old exams that you've taken this semester, I actually think you'll see it on there right now. But let me go ahead and just for kicks, oh no, it's gonna go to no, sorry. Oh, e-learning. So anyway, you should be able to find it either on the last page of regular exams, but I actually think the gas constant's been on your exam the whole time. And don't let me down now, 2019 exam. The reason why I'm doing this is because the other thing that should be there, boom, yes, giant table, standard reduction table. But what's also on there is the gas constant. Now, one thing that we do on here, and it's been like this all semester because I'm pretty confident that the gas constant's actually been on your exam the whole time. I might be wrong. I should say that. Could be wrong. But notice that we do just go ahead and give it to you in both the liters atmospheres mole Kelvin, as well as in the joules per mole per Kelvin. So it is your responsibility to remember that since we are dealing with thermodynamics and we're going to be dealing a lot with energy, you want the one with joules. So the units are on there, so you can see it really clearly. But you don't need to memorize it, that 8.314 is there. You do need to remember that you want joules. You're going to want joules for the whole exam. So you're not going to care about the liters and atmospheres. And hey, there's Faraday's constant, written with a whatever font that is, letter F. Written both in coulombs as well as in joules per volts. So some extra stuff, and this stuff might also be on there, although you won't need it. The other thing that will be on your exam actually is a giant standard reduction potential table, which somebody asked about. So let's talk about that. Let me see what I wrote down. So gas constant is going to be given to you. No worries about that. So standard reduction potentials. So whenever we say a standard reduction potential, there's a couple of pieces to that. So first of all, I'll go ahead and write actually everything out. Standard reduction potential. So standard. This is thermodynamic standard. Standard being 25 degrees Celsius, 1 atmosphere, 1 molar solutions. So standard does mean something. It does actually mean that if we have concentrations of something, they're at 1 molar. If we have gases, they're at 1 atmosphere. And if we're asked about a temperature, it's 25 degrees Celsius. Y'all have been assuming 25 degrees Celsius without being told otherwise for a while now. I know we tend to ignore it, but back when we were doing stuff that had to do with kW and the whole like 14 minus something, the whole reason you could use 14 was because everything was at 25 degrees Celsius or assumed to be at 25 degrees Celsius. So standard 25 degrees Celsius, it's back. It didn't really go away, but still. Reduction. This is the part where we're adding electrons. So no matter what we're talking about, I don't know, we'll grab gold. So no matter what we're talking about, it's going to be written as a reduction. So you're going to see these written with the electrons on the left-hand side of the equation every single time. So a standard reduction means that when you're looking at the list, flipping back over to that list, absolutely everything has electrons on the left-hand side as a reactant, every single one of these. So even though when you have a oxidation reduction reaction, something will be oxidized, something will be reduced. When we look them up on this table, they're all written as reductions. This really is a simplification because any two of these could be our 2 half reactions, our 2 redox half reactions. So instead of being like, oh, we're going to flip them halfway through the table, they're just all written as reductions. So that's the reduction part. Potential. Potential is the last word on here. Potential is actually going to refer to the that electromotive force, or really for us, this is an oversimplification ever so slightly. We're in volts. So when we talk about potential or the electrochemical potential, what we're trying to talk about is these numbers that are here on the right-hand side. So this E with a circle, that is your E cell or your standard electrochemical potential in volts. So the V is for volts, that's the unit. And what this is trying to talk about is this is talking about the, it's not really the likelihood to be reduced, but it's the voltage which relates somewhat to energy that you actually get from that half reaction when it gets reduced. So this is the amount of energy. Voltage is more than just energy, but the amount of oomph, the amount of voltage you get out of this when it's connected as a half cell. This value specifically actually goes with the one that is here in red, which is why this half reaction with hydrogen is 0. So this is one of those cases where all of these values are actually relative. They're all relative back to hydrogen. So something had to be chosen as the 0, and so hydrogen is chosen as the 0 because we can actually figure out the difference between any of these. But for all of these values, hydrogen is used as kind of the 0 point. So that's what they are. And we will also use those. Let's go ahead and do and address this unit 1 and do some thermodynamics, because I have a feeling we're going to spend a lot of time in electrochemistry. So let's go ahead and do a delta G, delta S, delta H equation. So for this, when they're talking about units, what they're typically referring to is, let's go ahead and say that, now is when I really wish I had prepped one of these, but I didn't. Let's go ahead and say, what is, I'll make this bigger, hold on. I prepped electrochemistry. What is the equilibrium constant? Equilibrium constant, there we go, for the following reaction, given the table of information. So I am just going to make everything up with A's and B's, but this will work. So we're just going to go with something like 2A goes to B, equilibrium constant. So it goes back and forth. And we're just going to give myself, these would be delta H of formation values. These would be standard entropy values. So I would have A here, I would have B here, and I'm going to go ahead and give myself a -12, and these would actually be in kilojoules per mole. Entropy values would be in joules per mole Kelvin. +2, +22, why not? Apparently I like the number 2. And this is going to be a -53, and this is going to be a +80.1. No, I don't want that 0.1. Sorry. Taking it back. Hadn't used decimals anywhere else. So then as we do this, since it's asking us for an equilibrium constant, that is asking us for K, but it gave us a whole bunch of thermodynamic data. So one of the ways we could get K from thermodynamic data, okay, the only way we can get K from thermodynamic data is to deal with something like delta G standard is equal to -RT ln K. This doesn't give me any sort of temperature. Oh, let's add a different temperature for kicks and giggles so I can show you one more thing. At 250 Kelvin. Yeah, 250 Kelvin, not 298, 250 Kelvin. So we're gonna pretend that was part of the question the whole time. At 250 Kelvin. Because there's something weird that we get to do. So this is going to be the goal. This is our -RT ln K. But in order to do that, we need delta G standard. And we don't have it. So we have to get it. And we're going to get it from this table of information. So we are going to do an awful lot of math for this. But that's okay, because we know how to do it. So in order to calculate my delta S of the reaction. All this is going to be is products minus reactants. So my product here is B. So that's 81 minus my reactants. But I'm going to use my stoichiometry. So that's going to be 2 times my 22. So I am going to use all of that information. So it's 81 minus 44. This is again that time where it's like, it's the only time I miss doing things live. I do like the recording. I like the recording a lot. But this is the part where it's like, oof, if I mess up on the math, I won't know for about 10 minutes. That's okay. So there's my delta S value, my delta H value. We're going to do essentially the exact same math, where what we're going to do is we're still going to do products minus reactants. So my product is B, that's this negative 53, minus 2 times negative 12. So that is negative 53 minus negative, so basically we're adding 24. So my value of delta H is a negative 29, and that is in kilojoules. Now the nice thing is that even on an exam, when we give you those sorts of values, they'll actually be given to you. So the fact that your value of delta H is in kilojoules, your value of delta S should be in joules. If you go ahead and look at the table that's provided, those units will be there. So the nice thing is that we don't actually assume that you remember those. We will give you those units. Just like when I was talking about looking at that back page and talking about our value of R, the gas constant, those units are still given. So even though, sure, if you do enough practice questions, you may very well remember what those units are. You can just look at them. Those units are given. Where was I? All right, so I got delta H and I got delta S. My goal is delta G. I'm going to get there. Delta G standard. So the reason why I wanted to do this is because this is going to be delta G standard at 250 Kelvin. That's what the problem asked me for. So that's the temperature I'm going to use, 250. Now, the weird thing here is that these values of delta H, of my enthalpy, delta H, and my entropy are actually from the 298. They're from the 25 degrees Celsius. As long as we haven't had a phase change, as long as everything is still in whatever phase it was originally in, and since I'm just dealing with A's and B's, we're going to assume that it is, the value of delta S and delta H change very little from temperature changes. I think at one point I got bored and did look up something, and basically they do change, but they change at so many decimal places out that it would round away. So for example, this negative 29 kilojoules, if we recalculated that, or if we had a table to tell us that for 250 Kelvin, we'd get a number like negative 29.002. And that is 0.002 would round away by the time we care about it. So we don't worry about it. But as mentioned, that's in kilojoules. And I should actually write out this equation. Don't just put the numbers in, write out the equation, be nice to them. Delta H minus T delta S. So we do want all of these values to be the same. It's really up to you. Actually, what would have been nice if I had put it in the table is if we had a whole bunch of multiple choice answers. Oh, we're going for equilibrium constant. Oh, it extra does not matter as long as everything matches. We're going to go to joules. Sure, we're going to go to joules. Dealing with big numbers is fun, right? So if you can't tell, it does not matter. So I'm just going to make this 29,000. You can go either way. It really does not matter as long as you are consistent. Minus 250, that's my temperature, times 37. That was my value of entropy. this is the part where I'm only excited because every time I make up a question and I haven't actually done it before, I get a little nervous. I'm going to do this twice. Hold on. 38,250. That seems reasonable. 250 times 37 was 9,250 plus 29,000. Yeah. Everything's negative. Everything's negative. Which should have worked because I have a positive value for entropy with my reaction. So I should have an increase in entropy. And then my value of enthalpy is negative. So this is an exothermic reaction. So increasing entropy of the overall reaction plus an exothermic reaction that should be always spontaneous or always favoring always a negative value for my delta G. So there should be favoring products, and that is what I have. This is still in joules. This is still in joules. Now that I have my value of delta G standard, I can go ahead and drag it over here. This is negative 38,250 equals negative RT ln K. For my gas constant, I'm going to grab that off the back page of the exam. And this is part of what I was double checking is, again, I need to make sure all of my units match. So the gas constant that we give you is here in joules. So again, that was where I was like, oh, it's equilibrium, so it doesn't really matter. But I also knew I was headed for joules with the gas constant. Now you can change the gas constant into kilojoules should you wish. So this could be negative. So negative 38,250 is equal to negative 8.314 times 250 is my temperature in Kelvin times the natural log of K. Divided by, so my negative signs will cancel out. And I wind up with positive 18.4. That's fine. It's equal to the natural log of K. When y'all are looking at your calculators, you should be able to find that right above the natural log button, this ln button is how you get out of the natural log. It's E. Notice that my negative signs went away. I have a positive 18.4. So this is going to be E to the positive 18.4 is equal to K. That should be pretty gosh darn big. Whoa. Oh, in scientific notation, it'll look a little better. Still pretty big though. 9.82 times 10 to the 7th. Which should also match my value of delta G standard was relatively big and negative. So negative delta G standard should have been product favoring. And here I have a large value of K also favoring my products. So that also tells me that we got through all of the negative signs on that problem just fine. Okay. So that way we did. So hopefully that helps with the units. Again, as long as everything matches. The other thing to keep in mind is since most of the questions are multiple choice, just kind of keep an eye out for what the multiple choice answers are in. Again, those actually all do have units. When you have some free time, go back and look at your old exams, and what you'll find is that as long as the final answer needed a unit, values of K don't have units. But if there was a unit in there like molarity, then that unit was always actually on those answer choices. I know that sometimes when you're like in the moment of the exam, you don't always think about, you don't always realize, but they are there. So you can always, when you're wondering like, gosh, what unit do I need? Either make sure they match or look at the multiple choice questions, the multiple choice answers and see what those units are in, and that'll help you out. Okay, let's go ahead. I've done 0 electrochemistry. So desperately want to have, no, that's going to take me a long time. Let's go ahead and see where we're doing on questions. Don't question that one out. This one, that's the one I did. I haven't done this one yet. Yeah.
It looks like at the moment we only have one more question.
Okay.
And it is, can you go over basic, acidic, and neutral balancing half RxNs and overall RxNs.
Okay, absolutely. I actually prepared for this question. Mostly because I hate balancing. There we go. I was like, I know I prepared for this. Where's the one I prepared for this? This, by the way, will also, because I prepared for this, this is also going to lead us well into that example too. Don't forget that we also need an electrolytic one. Okay, so we are going to do this guy. Chromium solids plus the sulfate anion, aqueous. I will write out the states of matter for now. We'll see if I fall off and stop that. There we go. And we are gonna, we're gonna balance this. I really don't want to do this twice. I'm gonna have, we'll balance this in base. We'll balance in basic conditions. Okay. So first off, in order to balance, what we're going to do is we're going to balance the half reactions, which means I need to put this in half reactions. When you're looking for half reactions, what you're going to look for is we're going to try to ignore oxygens and hydrogens, and we're just going to focus on things that are not that. So I've got chromium and sulfur and chromium. So we're just going to make those things match up. So I'm going to put my chromiums with the chromiums and put the sulfurs with the sulfurs, keeping that arrow in between whatever I have. So I've got chromium solid going to chromium 3+. And I've also got the sulfate anion. There we go. Going to sulfur dioxide. I am going to start to drop off my species just because I'm going to be writing a lot. So no matter what, we do need to make sure that those are balanced. So do I have the same number of chromiums on the left as on the right? 1 and 1? I do. Sulfur is 1 and 1? I do. Next is oxygens. You might notice that for the chromium reaction, there's no oxygens to worry about. So I'm actually going to leave that half reaction alone for a while. This sulfur one, though, I have to pay attention to. So we check the sulfurs. Now I'm on to oxygens. Those don't match, so I need to add water. That's not enough, though. So I have 4 here and 2 here, so I need 2 waters. Now that I've added water, I've also added hydrogen. So I have to fix this. So since I added hydrogens to the right-hand side, I have to add hydrogens to the left-hand side. So I have 2 times 2, which is 4 hydrogens, so 4 protons. Now, the nice thing here is when I think about sulfur, I've got 1 sulfur and 1 sulfur. When I think about oxygen, I've got 4 here and I have 4 here. And when I think about hydrogen, I've got 4 and I have 4. So everything is balanced right now. If I was balancing in acid, I would actually stop here. And then I would go ahead and I would add electrons and work on balancing electrons, and I'd keep going. But that's not what the question said. The question said basic conditions. Protons, those are acidic, so I have to fix this too. But the thing is that I want to keep the fact that everything's balanced. So right now, all of my elements are balanced, and I want to hang on to that idea. So I am going to add something, but whatever I add next, I'm going to add it to both sides so that I keep my elements balanced. So I'm going to add 4 hydroxides. The whole goal is to neutralize whatever that was and keep everything balanced. So we add to both sides. It's the only time that we do that, and only if we have to balance in base. If you had to balance in acid, we wouldn't worry about it. We'd already be done. But since we're balancing in base, we're also not done yet. Because since the whole idea of adding the hydroxide was to neutralize the acid, I need to put that in there. So really, this is not for protons and for hydroxide. That's actually for waters. So I'm just going to rewrite my entire reaction. Even though we haven't dealt with the sulfurs in a while now. Because the whole point was to neutralize the acid. So now I don't have any acid. Woohoo! Success! I got water on both sides though. That's kind of clunky and yucky. So what we are also going to do is we are going to fix this. And so I have 4 waters here and I have 2 waters here. So for the sake of if somebody asks me about this, it's going to make my life easier. I'm going to rewrite this again. If I was doing this or to get the answer, I would not actually rewrite this. I would just cross out the coefficients. But if someone asks me about this balancing mechanism, I'm gonna be real sad if I do that. It's gonna be really hard to go backwards. This is a little easier. So basically we got rid of the 2 waters on the right-hand side and we subtracted 2 waters from both sides. So I get 4 now on the left. I have no water on the right. Now I'm done with the half reaction, except we haven't looked at electrons yet. So there's 2 different ways to figure out the electrons. I'm gonna try to do it the way Alex does it. You can hear the tone in my voice be uncertain about this. Actually, we're gonna do the no. I'm on this one. I can do this. So this is the way Alex does it. I don't know how I feel about this. So Alex is like, okay, so what's the charge over here? So I have one species with a -2 charge. So right now I've got -2 here. Then over on this side, I have 4 hydroxides. So that's a grand total of -4. So in order to balance my electrons, I'm just going to add 2 electrons over here. So that way I have plus 2 electrons, so that this is also -4, and then they match like that. That's the way Alex does it. If you can't tell from the sound of my voice, I'm not a big fan of this. There are reasons I'm not a big fan of that. Here's the way I would actually do it. I would actually do it like this. Oxygen, that has an oxidation state of -2. There's 4 of them. So I have 4 times -2 is equal to the overall charge, which is -2, plus I've got 1 sulfur, which I don't know what its oxidation state is. That's X minus 8 is equal to -2. X is equal to +6. So that then is the oxidation state of my sulfur. Over here, on the right-hand side, this has oxygen, again, it's going to have a -2 oxidation state. There's 2 of them. This is going to have an overall charge of 0. I have 1 sulfur. So this becomes X minus 4 is equal to 0. X is equal to +4. The oxidation state of this sulfur is +4. So I'm trying to go from +6 to +4. To make that balance, I need 2 electrons on the side that has the +6. Notice I get the same answer. The reason why I like the oxidation state way better is because I don't have to get the balancing correct to get the electrons correct. So this actually allows a really nice double checking mechanism in my work. So while I understand that if speed is the only thing that you're looking for, then by all means, this dealing with the positives and negatives of the whole left-hand side, right-hand side can certainly be faster. I would just be wary because that counts on the fact that you got all of the balancing correct and that you're carrying your charges correct. And I love you guys. You guys are wonderful, fabulous people. But if you didn't copy down that -2 on the sulfate anion, you'd get the electrons wrong. Just saying. So just be aware, there's always pros and cons to every method. Doing oxidation states takes longer. It does. Anyway, so 2 electrons. Oh God, I'm not done yet. Sorry. Apologies for that. Well, that's the half. I did, it's the half reaction. I didn't do the whole thing yet. Now, I will say something before I continue. If the only thing that the question wants to know is about waters or hydroxides, you can actually stop here, right? Because there's no waters and hydroxides on this other one. It's just the chromium and some electrons. So if the only thing you're being asked about is water, then you're finished. And we can just confidently say that there are 2 waters on the reactant side, and you're done. So we didn't actually even have to do the electrons if that's the goal. Actually, no, I'm lying. Oh, I'm lying. Oh, I'm wrong. I'm wrong. Sorry. So we do have to do the whole thing because we may have to multiply everything by something. Oh, do we have to multiply something by something else? Neutral on this side plus 3 electrons. No! Why did I do this to myself? This is so long. Okay, here's 3 electrons. This is the reason why my husband finds these exam reviews to be very amusing. 3 electrons over on here, and I have 2 electrons over here. Oh, we have to do more math. I wrote this problem. What am I doing? Anyway, so good news. I have found the place where everything would be wrong if we tried to shortcut. So we're not going to shortcut anything. Yay. So I have 2 electrons with this half reaction. I have 3 electrons on my other half reaction. My electrons have to match. So in order to do that, I'm just going to multiply both equations by something. The one with 3 electrons gets multiplied by 2. The one with 2 electrons gets multiplied by 3. So this chromium reaction then becomes 2 chromium solids goes to 2 chromium aqueous plus 6 electrons. This reaction down here, I'm going to be using a feature of OneNote where I copy and paste the whole reaction. So my apologies that this is going to be in an awkward place and I'm going to move it. Where am I going to, actually, no, I'm going to put it over here. I'm still going to move it. 3 times 2 is 6 electrons, plus 3 times 2 waters is 6 waters, plus 3 times 1 sulfate is 3 sulfates. It's supposed to be sulfate, plus 3 times 1 sulfur dioxide is 3 sulfur dioxides, plus 3 times 4 hydroxides is 12 hydroxides. Okay. I am actually going to move this stuff so that I can make something line up that makes me feel better. No, all I'm doing is moving some things around because part of what I want to do is I just want to line up my arrows. So this is part of the reason why whenever I do balancing, it usually takes me a minute because I really like my reaction arrows to be lined up. It helps me identify where all my products are, where all my reactants are. So I really like my reaction arrows all lined up. Add them together. My electrons cancel just like they're supposed to. Thank goodness. Otherwise, I'd be very angry. So 2 chromium solids plus 6 waters, which would be as a liquid, plus 3 sulfate anions, which are aqueous, goes to 2 chromium 3 plus aqueous plus 3 sulfur dioxide. It's a gas plus 2 hydroxides aqueous. Doesn't even fit on one line anymore. Also, that sulfur dioxide as a gas, in case you're curious, it was actually labeled as a gas way up at, scroll up. So in my notes, it's a gas. And I understand that you may be like, how do you know? You know, because the problem actually told you 15 minutes ago. That's how you know. That's the whole thing. So speaking of the number of waters, if the question was number of waters, now my number of waters is 6. So that's the reason why I said something and then freaked out because of what I had said was wrong. So the number of waters is there are 6 waters on the reactant side. That's the answer. 6 waters, reactant side. Got to make the electrons balance. Got to make the electrons balance. Oh, that was long. So one of the other questions that was asked was about things like galvanic cells and doing some examples. So I think dealing with E-cell. So actually I'm going to scroll back up to double check what that question said. Example, conceptual and calculation, galvanic, voltaic, electrolytic. So sure, let's go ahead, since we have this lovely giant reaction. We did already figure out where our electrons were. So what I am going to do is I'm actually just going to go back to that half reaction point. And we're just going to grab those 2 half reactions. I'm actually going to unbalance them. But we have chromium solid going to chromium 3+, aqueous, and we had sulfate 2- going to sulfur dioxide. And I do want my electrons, +3 electrons here, +2 electrons here. That's fine. I know that they're not balanced. +4. +2 waters over here, +4 hydroxides over here, balancing the base. So some things that we can do. First of all, those are my half reactions. When we started way over here, everything was all together. So I also could have started from this point and I can copy and paste this. Please make my life easy. Yes. Okay. So granted, we've already solved for those half reactions, but I could have started from this thing and I could have just asked, well, I should do a calculation with this one. I should have asked, what is E-cell? Standard. If this is what my question is, then I need to do a few things. One, I do need to identify what's being oxidized and what's being reduced, because that's going to matter in E-cell. Now, we've already solved for the half reactions, but we're going to go ahead and still talk through this. So my chromium goes from +3. So my chromium goes from neutral to +3, means my chromium is oxidized because it's going from neutral at 0 to +3. It's going towards the positive side. So chromium is being oxidized. You could have also seen that in the half reaction here where I have my 3 electrons on this side. So this is my oxidation reaction. Now, in order to figure out that sulfur is being reduced, that would be another time where we could go back through all of the oxidation numbers that we did to look at the fact that my sulfur is going from +6 to +4. I'm not going to redo that math since it's already done for you. But I can look at my number line, 3, 4, 5, 6, and it goes from a +6 to a +4. So even though I know all the numbers are positive, I can see that my sulfur values point towards the negative end. -1 would be over here. So I can look at the direction that my oxidation numbers are going in to tell me what's being oxidized and what's being reduced. So since I now know that, what I'm going to do for E cell is my E cell standard is going to be equal to whatever number is being reduced minus the number of the thing that's being oxidized. Just pulled off the table. So that means I've already figured out that I want my chromium to be here and I want my sulfate to be here. So that's the goal. So now I'm going to go ahead and go to my table. Now I'm going to cheat a little bit because since I wrote this problem, I already have some things labeled. But this actually brings me to a quick point. You might notice on the screen that I have some straight lines and I have some squiggly lines. Because you're going to be using this giant table on the exam and you're going to be doing multiple reactions with it, may I encourage you to have a system that helps you identify which values you're using. So for example, the squiggly lines go to iron 3+ and iron 2+ and cobalt, which is a different problem I prepped. The straight lines go to sulfate and the sulfur dioxide, and they go to the chromium reaction. So granted, there are different ways to do it, but that's my personal strategy for being able to figure out where things are. The other thing, which is difficult to show y'all on the screen, but the other thing that I need to do tomorrow, hopefully I remember, because there's lots of numbers, I usually also recommend you take one of those pieces of scratch paper off of your exam and use it as a straight edge to make sure you pull the correct value. So basically here I'm cheating and I'm pretending that the bottom of my screen is a piece of paper so that I can line something up. So that way as I'm going across, I can see my chromium value is -0.74. I know it's really small, but again, it helps me keep everything in line because this is the table we're going to pull for y'all. Again, you can see from the olds exam, what we also do though is we do take those numbers off of there. So you can't have the numbers anymore, or the arrows, pardon me. So there are 2 arrows to tell you information and we take those away from you. But yeah, so I recommend some sort of doodle that makes your life easier. If you want to do that in color, you can. If you want to bring highlighters, you can. So there's lots of different things you can do. I just use squiggly lines. So I usually have squiggle lines. What else do I do? I'll do these kinds of things. I'll do 2 lines. I will sometimes do a slow wavy line and a fast wavy line. Anyway, I've got lots of different lines that I use when I'm doing this to help me out. So what was the question we're working on? Oh, I'm in OneNote. Like, why don't let me go to my other thing? Because I'm in OneNote. I want E cell. So therefore, I need my chromium reaction. It's this -0.74. And my sulfate reaction, it's this +0.2. So I am doing things as I'm just pulling stuff off of the table. For those of you in Dr. Diekman's class, this is not the way he does stuff. For those of you in the other classes, I do not know what they do. This is the way that Alex does it, and this is the way most of y'all wind up doing it because it's the way that Alex does it. I will make another point in just a moment though. So this is a positive 0.90 volts. So there's a calculation. Now, the other thing that we could have asked is this for a galvanic or an electrolytic cell? So a quick note on, or voltaic. So a quick note, let's make the Venn diagram, shall we? Don't we love Venn diagrams? Galvanic, it's supposed to be the, y'all have noticed by now that my spelling is not great, right? I feel really bad because, man, in like 6th grade, I was amazing at spelling. That is all gone now. Thank you, spell check. So galvanic and voltaic are both examples of spontaneous cells. So those two are actually the same thing. A non-spontaneous is called an electrolytic cell. Electrolytic. The generic term is electrochemical. So oftentimes the question will read something like, an electrochemical cell is set up with the following reaction. Then we could actually ask you if it's spontaneous or non-spontaneous. We could ask you if it's a galvanic cell or an electrolytic cell. We might also use the word voltaic cell. It just depends on who wrote the question. So you are responsible for all of this language, as it's language that we might either use or ask you to use. Because what I got out of this was a positive 0.9 volts, I expect this to be in the galvanic voltaic set. So positive voltage, galvanic or voltaic cell. Those two mean the same thing. There's two different words for it. Thank you, history. If it was negative, this would be an electrolytic cell. So that gives some of that information. Oh, remember one of the other things I want to talk about. So in calculating E cell, notice how I've written this, that this is the reduced species minus the oxidized species. Everything off of the table is a standard reduction value. So back, I don't remember now when, the question was something about the standard reduction potential, and the comment was basically everything on the table. So all of these, no matter what, all of these. So all of these are reduction potentials. So every single one, these are all reduction potentials. All of them, potentials. So when I'm writing my little equation and I say one minus the other one, I'm saying that all of those in the subtraction set are actually reduction potentials. So these are both reduction potentials because I just pulled them off the table. Just pulled off table. I didn't flip any signs. I didn't do any of that. Now, realize that if I wanted the oxidation potential, so my reduction potential for chromium 3+, as it is pulled off of the table, is negative 0.74 volts, and that is its standard reduction potential. If I wanted its oxidation potential, then what I'm asking for is I'm asking for what happens when you actually flip this thing around. In that case, I'm actually asking for the sign to flip. And this is the reason why you can also find E cell standard being the reduction potential plus the oxidation potential. But if it's asking for oxidation potential, that means you have to write things as an oxidation reaction, which will involve flipping the sign, since the table that we give you is a standard reduction table. Now, why would you care about this? You would care about this if, and only if, the question asked you for the standard oxidation potential. So if it asks you for your E cell standard, you probably don't care. You're going to calculate that however you were taught, which might be from class and it might be from Alex, don't know. But your standard oxidation potential is just flipping the sign off of the standard reduction potential. And remember, we are just going to pull this table off of your textbook. And while we are going to get rid of the two arrows on either side, notice it still says at the very tippy top, standard reduction potential. Also, they're all written as reductions. So there's lots of different ways to remember that and keep that in mind. Okay, we've done balancing. I've done galvanic and voltaic. I've done calculating E cell. Oh, let's do a line diagram. Yeah, let's do a line diagram. Then I'll take questions and see how we're doing. Okay, so actually, I'm gonna go way back up here. Oh no, I don't. Ooh, what do I want? I do. I want this one. Sorry. This is that weird time where I'm trying to make certain that I'm picking things of an appropriate complexity is what I'm. So actually, I'm going to do a different one. So if we had a different reaction, yeah, I want this one. So if we had a different reaction, I'm going to write this one. 3 plus cobalt solid goes to cobalt 2 plus iron 2 plus. And what I actually want to do now is I want to write the shorthand or the line notation. When I do this, it would help if I wrote aqueous in here. When I do this, one of the nice things is that this is just read left to right. I do also put oxidation on the left and I put reduction on the right. So I do have to identify those. So I'm looking for my iron. This one's a little bit clearer just because there's no oxygens involved. So here, 1, 2, 3. Here I'm going from +3 to +2. My little arrow points towards the negative side. So this is getting reduced. Then my cobalt is going from 0 to +2. So my cobalt is going towards the positive side. So my cobalt is getting oxidized. So my cobalt, therefore, is my oxidation reaction. So this is cobalt solid to cobalt 2 plus aqueous. I don't know, should be parentheses, not a line. With a salt bridge in between, to left to right. Iron 3 plus, iron 2 plus. So this is one of the only, so I wanted to do this as an example for a couple of reasons. One, while we don't always cover it in class, and we won't test you on this, by the way, we'll just do it. So the only reason I wanted to show this to you is if we do it for you, don't worry about it. Use a comma if you're in the same phase. Use a line if it's a different phase. So honestly, just typically we are changing phases, and so you don't usually see the comma utilized because we're almost always going from solid to aqueous or aqueous to solid or gas to aqueous. We're usually doing something like that. So a lot of times you see the line. But if everything's aqueous, use a comma. But since everything's aqueous here, there's actually one more thing we'd actually add in here, which is an electrode. Because you need some sort of electrode because you need a solid to attach the wire to. Now, one thing I do want to point out with this particular problem is I actually didn't analyze this for galvanic or electrolytic. It just said, hey, here's a redox reaction, write this as line notation, and I did. We didn't go back and double check any values. We didn't calculate anything. We just wrote stuff down. And that's fine. That works fine. So just be aware that a lot of times when we're in class, we have a tendency to do a lot of analysis because we're trying to emphasize how well things go together we're trying to take a look at how I can know multiple different things from a small amount of information. But if you're just given a redox reaction and then it tells you to write the line notation for it, you don't need to calculate anything. So I realize that there's a lot more conceptual stuff we could do, but there's at least an example of a calculation question and a line or shorthand notation question on there. And I've been talking for a while, so I'm going to go ahead and pause again and see how we're doing on questions, but I'm also going to scroll back to where my question stuff was, because I like my questions to be in the same location. All right, I am ready when y'all are.
All right, looks like we got a few new questions in. First one is, if you use KJ or J, do you still get the same K? Next one is,
okay.
Can you go over a standard cell potential example?
Okay.
All right, next is, could you over question 31 on the S19 exam, please?
Okay.
Next one is, how do we know if a certain voltaic cell has a higher voltage than another voltaic cell, which is number 1 on the 2019 exam?
Okay.
And the last one at the moment is, how do we determine the strongest reducing agent?
Okay. So to the person that asked for a standard cell potential example, I think I already did that because we did that with the sulfate. Actually, we'll just do it with the one we just did. Since I made a big deal about the fact we didn't analyze it for voltaic. So as far as standard cell potential goes, I think I'm answering this question right now. If I'm not, and I'm wrong, put something more descriptive in the chat or tell me what equation you're trying to get me to use. So we already analyzed this one for which one's oxidation and which one's reduction. So since I have that information, we're going to do the standard cell potential is equal to whatever my reduction number is minus whatever my oxidation, my species oxidized is. We already figured out reduction is the iron. So I'm going to go to this. Again, I have cheated a bit because I already have these labeled. So my iron to iron is positive 77. Iron 3 plus to iron 2 plus. When y'all are on this table, iron shows up in a bunch of different places, but I need the one that is all aqueous. That's what I want, so that's what I'm going to use. Positive 7. Hey, sorry, that hey was to me. Oh, that's what this was for. Anyway, sorry. Reduction potential 0.77 volts, positive here. Oxidizes cobalt. No, not cobalt. No, which one do we use? Which one do we use? Oh, it is cobalt. Okay. Sorry, there's lots of C's. I got nervous that I needed chromium. I do actually want the cobalt one. Where is the cobalt one? Squiggle line, negative 0.28. Negative 0.28. Also, that was just because my exclamation was because I worked out a complicated problem that if nobody asks me about it, I will do in the follow-up video because it's a lovely problem. So that is a standard cell potential problem. That is a standard cell potential problem. If you're looking for something more complicated, you probably either want to ask me about delta G and cell potential, and equilibrium. You probably want to ask me about that if you're looking for something more complicated, because otherwise that is standard cell potential. A positive sign, galvanic cell, or voltaic cell. Same cell, two different names. I am so sorry about that. Not what we were doing. Oh, that's why I wrote down the questions. By the way, I am like this in real life. So I think I answered this one. Someone is probably now feverishly typing into the chat. Okay, kilojoules or joules, same value of equilibrium. Yes. As long as you are consistent, it does not matter. So actually what I'm gonna do is I'm gonna pick up here, which is a problem we did a while ago now, but this one is all in joules. So this one, we went ahead and had a delta G standard of negative 38,250 joules. And that's what's utilized over here in blue. Then 8.314 is also in joules. Looking back at the potentially useful information page, that's in joules. So all this work here done in blue is in joules. What we're going to go ahead and do is recalculate this, but recalculate this in kilojoules. So just going to come over here. Here's my value for delta G standard, but I want this in kilojoules. So I want negative 38.25 kilojoules is equal to negative, this would be R, but now R needs to be 8.314 times 10 to the negative 3 kilojoules. So 8.314 would be in joules. So therefore I'm dividing it by 1,000 to get myself to kilojoules. Yes, I am doing that relatively quickly to demonstrate. So I'm not doing a very good job of demonstrating changing units. If you do need that done better, let me know. I'll just do it real quick. 8.314 joules. There are 1,000 joules in 1 kilojoule. So that's how we're doing that math. So we're dividing by 1,000 when we go from joules to kilojoules. Metric conversions, it's been a while. So now when I do this math, the thing is that because both of them changed, I still have that factor of 1,000. So I just have to make sure that I put all of it into my calculator correctly, but I should actually get the exact same number that I did before. So now I have two negative signs cancel out. I get 18.4 is equal to the natural log of K. Everything's positive, so this is e to the positive 18.4 is equal to K. Just look at a really giant number, 9.82 times 10 to the positive 7. So I'm going to scroll back and see if it's the same. It's the same. So again, the point is to make sure that those match. So you will likely have the control over which way you go. And again, just remember that even though you may have done enough example problems that you may very well have that 8.314 memorized, that 8.314 is in joules. So if you're going to use 8.314, that's in joules, not kilojoules. But that information's on the back page of the exam. So if you're on the exam and you don't remember, you know the number, but you don't remember the unit, just look at the back page. It'll tell you which one it is. And as long as they match, you're fine. So whether you want to change your value of R to be in kilojoules, or whether you want to change your value of delta G standard to be in joules, doesn't matter as long as they are the same. So they do need to match, but as long as they match, you're going to be fine. Okay. Strongest reducing agent. Let's do that one. So first of all, We didn't talk about reducing agents at all. So first of all, we have to talk about what that means. So grabbing this stuff. When we talk about something that is a reducing agent is what allows reduction to happen. So a reducing agent allows reduction to happen. If something's going to allow reduction to happen, it needs to give away electrons. That therefore means it's the species oxidized. So this language is terrible. You do need to practice it. Now, there's a couple of things with this that are really important. So when we turn to the table, when I say that I want a reducing agent, I want something that's easily oxidized. So the strongest reducing agent, and you can actually see there's arrows on here to help with that. Those are the arrows that will be going away, by the way. When I say I want something that's going to be a reducing agent, something that can be oxidized, when we look at this table, we actually didn't talk about this yet. When I look at this table, realize that the tippy top of this table is fluorine. Fluorine desperately wants more electrons. So fluorine, the gas, is easily reduced. When I look at the bottom of this table, I have lithium. Lithium as a solid is easily oxidized. Now, here's something else about me saying that. This does help you orient on the table. Top of the table, more likely to be reduced. Bottom of the table, more likely to be oxidized. But notice, even though on the exam we're going to take them away from you, these arrows talk about agents. Realize that lithium positive versus lithium as a solid. Only one of these two things can be a reducing agent. Because when we say reducing agent, we want something that can give away electrons. Lithium solid can give away electrons. It's currently neutral. We can look at the table and lithium solid can go to lithium plus an electron. This can be, so lithium solid can be oxidized. It can give away electrons. But lithium plus doesn't have any more electrons to give away. It already gave them away. So lithium plus can't help you out as a reducing agent. It already gave away the electrons. It's totally happy like it is. It doesn't want any more electrons, but it already gave them away. Doesn't have them. So lithium solid has the electrons. Strong reducing agent, no problem. Lithium plus, not so much. Doesn't have anything to help you out with that. So lithium solid, strong reducing agent. Lithium plus has got nothing. Not helpful at all. So keep in mind when you're looking at the table, you also need to look at what state these things are in and if they have electrons to give away or not. So that reaction is set up to tell you information. So you do need to read the whole reaction as to what's happening. So a reducing agent can give away electrons. So your lithium solid can do that. Your lithium 2 plus already did it. Can't do it anymore. It's out. I a lot of times think about this as if you're going to borrow money from somebody, you got to go to the person with the money. If you hit up the person that's either already lent out their money or they don't have any money, they can't help you. Like they may be a very nice and lovely person, but if you hit up the person that's already given away all their money or doesn't have any to spare, they can't help you. So you're looking for a reducing agent. You want the things that can give away electrons. same thing with the oxidizing agent, but reversed. If I want an oxidizing agent, then I want something that can take electrons. So in that case, if I want things that can take electrons, I want stuff over here. I want things that are on the left-hand side of this reduction potential table that has the ability to take more electrons. So I want that like fluorine gas. I don't want the fluorine minus. Because my fluoride ion already took the electrons. It's happy. I want the thing that's neutral. I want the thing that wants to still take electrons if it's going to be an oxidizing agent. I don't want the thing that's negative. I don't want the thing that already has the electrons. I want the thing that wants more. So when we do oxidizing agent and reducing agent, not only does that have to deal with top of the table, bottom of the table, because it does. So you still want to analyze things for where is it on the table, because the strongest oxidizing agent will be closer to the top, the strongest reducing agent closest to the bottom. But you also have to pick for an oxidizing agent something on the left-hand side of the reaction, or a reducing agent something on the right-hand side of the reaction, because it has to be able to actually do something. So practice helps. Where are the questions? Yeah, that is definitely a favorite exam question. Speaking of exam questions, that's all I have left are exam questions. I am actually going to look and see at least what these are, because I want to see if these are something that we're testing on this semester or not. 31. Uh-oh. So I wrote down that one of them was supposed to be number 31 on the spring 19 exam, but the spring 19 exam only goes to 24 questions. So I don't know what you're talking about now. I will actually, since this one's on the screen, by the way, this is a nuclear reaction. This is something that would be on the final and would not be on exam 4, in case you're curious. Wonder if it's 13. Let's see if it's 13. 13. Make this smaller so I can actually see the whole thing at once. Calculate the value of the cell potential at 25 degrees Celsius for the following unbalanced reaction and conditions. Yay! That's the really complicated one that I prepared for too. So if it's 13 that you want, we won't do 13 on this exam review, because I like people that if they wanted to try this question out on their own, that they have a chance to. So I'll do 13 in the follow-up video, because I have a version of this I made myself. Oh, this thing not on the exam. Look at that. There's a Nike swoosh graph. Not on this exam. No Nike swoosh. Voltaic voltage. Voltaic voltage number 1. What's voltaic voltage mean? Oh, okay. Number 1. I will do number 1 in the follow-up video, because again, it would be better if you guys got a chance to do this one on your own. But the way that you do this, because it says using the metals together with their 1 molar salt solutions. It's telling you that information because 1 molar salt solution tells you that you're at standard conditions. So you're not trying to actually do a lot of calculations. You're already at standard conditions. So all you're going to be using is the values on the standard reduction potential table. So there are 2 different ways to do this. I will do them both in the follow-up video, but for now, I'm just going to give you guys that hint that because of the 1 molar salt solution, you're going to use that table, and you're just going to use the standard reduction potential values off of that table is what you're doing. That's how that one works. I know it didn't entirely answer it, but again, I like folks that if they haven't gotten a chance to do the old exam yet, to do the old exam. I am, since I alluded to it twice, I'm going to go ahead and do the problem that I prepared that is somewhat complicated. That is a good mimic for number 13 on the exam. Where did it go? Not that one. This one. So this actually uses the same iron cobalt reaction because that's where I got it from. But what it's going to ask, and I'll blow this up in just a minute, what is E cell when, and then I apologize that I don't have the superscripts because I didn't do this ahead of time, but I wasn't confident I was going to get to this. Those equals 0.01, but is what I stuck with, right? Yes, it is. And Fe3 plus equals 0.5 molar. Oh, I should have molarity in there, molar. Make it big, make it big. Boom, big. I know it doesn't bother y'all, but it bothers me. Oh, superscript, superscript. This also bothers me because one of my other classes, I edit people's science writing. And it bothers me when science majors don't use superscripts and subscripts because y'all are science majors. You guys should have seen this before. But that's also a senior level class. So in a senior level class, I also care more. So this is supposed to, for the reaction that we've been doing. So this should also say for the following reaction. For the following reaction. And it's the same one that we had up before. So this is going to look a little bit similar to previous questions because this is actually the reason I had this reaction prepped. So, couple things. One, the old exam question was actually nicer than I am right now because the other question told you that the reaction wasn't balanced. This one's not balanced either, but it doesn't say that. So I don't know who's writing this kind of question on the exam and if they were nice or not. Wasn't me this time. I wrote other questions, but this is asking for E cell. The other thing it's asking for is, notice there's no little circle. There's no standard symbol. It's not there, which means, but there's also no temperature given. So we are going to assume 25 degrees Celsius. We are going to make that assumption, but there's no standard symbol there, which means we have to use the big version. Equals E cell standard minus 0.0592 divided by N times log of Q. So, a couple things. There are, so because we are assuming 25 degrees Celsius, I'm using this version of the equation. We could also use the other version that is the E cell is equal to E standard cell minus RT in F ln Q. So we could have used that because we're at 25 degrees Celsius using the shorter version. Then from there are three different things I have to find. I need to find E standard of the cell. I need to find N. I need to find Q. I got three different values I'm looking for. The exam problem was also nicer because it gave you E standard of the cell. We actually already solved for that. So I'm actually going to cheat a little and scroll up because, why, look, it's the exact same question and the exact same reaction. And we already solved for E cell. It's positive 1.05 volts. So same reaction. I am going to just grab that. So I found one thing, because we solved for it earlier, we did pull those values off of the table. If this was an exam question, we would probably give it to you to save you some time, but you should also know how to pull those numbers off of the table, which in the recording you can reverse it because we did that earlier. N, the heck is N? We haven't done one of these yet. What's N? N is the number of electrons transferred, which means I need a balanced reaction. Now, we can look pretty quickly and see if my reaction's balanced or not. The way we're going to figure that out is we're going to look, and here I have +2 plus +2, which is +4. Over here I have +3. This is not balanced. Now, I can't just add electrons to the whole balanced equation. That doesn't work. So I do have to think about these as half reactions. Now, granted, because of E cell, we could actually just flip over here. Thanks, OneNote. The hidden thing. We could actually flip over here, and if we can find them, here is my cobalt reaction. I know it's very small, but here's my cobalt reaction with 2 electrons. And over here is my iron reaction with 1 electron. But if they're not in the table, how would we know? So if they're not in the table, we would actually have to separate our half reactions and figure this out. So this is cobalt solid goes to cobalt 2 plus, neutral and 2. That means 2 electrons here. Iron is iron 3 plus and iron 2 plus. So iron 3 plus, iron 2 plus 1 electron here. That does not balance 2 and 1. So I'm going to multiply everything by 2 on the bottom reaction. So in my balanced reaction, I have 2 Fe3 plus cobalt solid goes to cobalt 2 plus 2 iron 2 plus. So I found N. N is the number of electrons transferred. It's the number of electrons that would be in the balanced reaction. So I found N. Collecting numbers, we're doing really well. So N is equal to 2. That's what I wanted. Then the last thing I need is Q. I'm going to get Q from the balanced reaction. So Q is cobalt, not carbon monoxide, cobalt times iron squared. There's a 2 here. There's a squared term there. Divided by iron 3 plus squared times 1. Remembering that solids are not in our Q expressions, they're also not in our K expressions. Equilibrium, we're still using it. My class, I made a big stink back in like February when we started the equilibrium unit, and I was like, so once we do equilibrium, it never goes away. And I meant it. And I get this kind of like smug look on my face. It doesn't, anyway. So I need a value for Q. Let's go back up and see what numbers I have. Cobalt 2 plus and my iron 2 plus are 0.1 molar. Iron 3 plus is 0.5. Okie dokie. So I'm just going to plug those values in. Oh, look, my 2 pluses are on top. My 2 pluses are the same value. Sorry for the scrolling back and forth so much. So that's 0.01 times 0.01 squared divided by 0.5 squared. So my value for Q, this is 1 times 10 to the negative 6 divided by 0.5 squared, 0.25. That is 4 times 10 to the negative 6. I'm going to double check that because it was earlier by 0.25. Yay, okay. It's that time where if this number is wrong, everything else is going to be a little wrong. So that's Q. We found all the numbers. I know you're excited. We found all the numbers. Now all we have to do is plug them in. So what? Where did it go? This thing that I've scribbled all over. So as you might imagine, I'm going to redraw this. I'm going to rewrite this. But I have my E cell of 1.05 volts. I have my N value of 2. This thing in green is part of the equation. So this is that time where if we're using this whole thing, I have that memorized. Log Q. So now it's that time where I look down a whole bunch because I wrote this out earlier. And I did actually double check this math. 1.05 minus 0.0592 divided by N, which is 2 times the log of Q, which we found to be 4 times 10 to the negative 6. It's just math now. This is 1.05 minus negative 0.1598, which means that I add those things together, I get a final voltage of 1.21 volts. Done. So this equation, so for those of you that I've said this to before, or you've heard me say this before, I'm a big fan on exams of knowing things like which questions you like the most. So questions that you know how to do them, you know they'll be relatively straightforward to do those first. Ones that you know will take longer, I'd recommend you do those last, because all the multiple choice are worth the exact same number of points, and it's always worth taking a look at the back page of the exam to know what's coming. This kind of question tends to be one of the longer questions because unless we gave you the value of Q, which we might have, but unless we gave you the value of Q, figuring out Q takes some time. You have to figure out if the reaction is balanced, or if we flat out told you it wasn't, you have to balance it. You have to write your Q expression, plug in all the numbers and get Q. And that's just for Q. That is ignoring the fact that we also had to do some math to get in, or pay attention to get in. We figured out when we did our balanced equation. And either it's given the problem or we have to go find the standard E cell. So this is the kind of problem that is usually one of the longer ones because of how many numbers you have to pull together. So aside from the actual exam questions, which are going to be in the follow-up video because that is my choice and I get to do that, I ran out of questions. So it's time to ask for questions again.
It appears we have just one more at the moment, and
okay.
It is how do we know where electrode goes?
Okay. Pretty sure I know this one. So I think that is in reference to, where did it go? When I was doing the line cell notation. So for the same reaction, believe it or not, the cobalt and iron reaction, and then I wrote the line notation and I just had cobalt solid on the left here, and I just stuck platinum on the right, like boom, there it is. So let me actually do a better job of this. So when you're doing line notation, so part of the reason why this worked like this, so granted, 2 plus aqueous, saltbridge. So let me actually point out a couple other things that are in here, but I didn't mention. I put the states of matter. That's aqueous. Oh, see, there go my states of matter. Aqueous, platinum. So a couple of things. One, whatever's here on the edges, these are my electrodes. Now, it just so happens that because cobalt is a pretty nice stable metal, using cobalt as an electrode is something that we can do. So even though it's participating in the reaction, it's still an electrode. If we were going to build this thing, I would actually have a block of cobalt that I could put in my electrochemical cell. There's my beaker. There's my other beaker. Here's my salt bridge. Here's a wire. But over here, I would need a piece of platinum because I need something solid to attach the wire to. So this is a wire. I unfortunately don't have any that aren't coated in something. But y'all have, I realize that we are all about wireless charging nowadays, but you can't tell me you've never seen a wire before. So when we say wire, I mean wire. I mean the thing that lets you charge your cell phone, unless you have wireless charging. Even then something goes to the wall to get the electrons. Oh, did I not mention electricity? This is all about electricity and electrons. We probably should have started with that. This is why I'm really glad that batteries are part of this unit, because I think I forget to say, by the way, electrons, charging stuff. That's actually what we've been talking about the whole time. It just hasn't been obvious. So, whoa, this is terrible. So anyway, so my electrodes are these things on the far end. Whatever's solid here are my electrodes. It's what we're going to physically attach the wire to. Then the other thing that is in here and sometimes can be in here, I usually just leave it out, but I also could have written in here, I could have written something like KNO3. I could have written salts in there. So there could be, so we could actually claim exactly what's in the salt bridge. We don't have to, but we can. So I could put KNO3 that would have been here in the salt bridge. So I've got my cobalt reaction happening over here. So I've got the cobalt solid going to cobalt 2+, and over here I've got my iron 3+ going to iron 2+. Because the reaction over here is all aqueous, this is happening, but it's essentially just happening against the piece of platinum. So I have iron 3+ in solution interacting with the platinum. So it's kind of like it's bouncing off of it. It's picking up electrons from that piece of platinum. So I get Fe2+ hanging out in solution. This cobalt electrode is actually degrading because it's kicking off cobalt 2+. So my cobalt electrode will actually get physically smaller as this reaction proceeds because I am generating cobalt ions in solution. Now, since we've drawn this much of the diagram, we might as well keep going. Since we're talking about what we're kicking off and what we're getting, notice that if this kept going, I'd get a buildup of positive charge here on the left. So I need a negative charge to combat that. So the nitrate from over here is actually going to flow down here to help balance the charge. So I have this +2 that's being generated by the reaction. I'm going to have a negative charge to help balance that out. So this over here, this is oxidation, anox. So this is also my anode. Over here, therefore, this is my red cat. This is a reduction reaction. My cathode is the piece of platinum because the cathode is the site of reduction. So I have anions move towards the anode, and I'm going to have cations move towards cathode. So here, my iron 3+ is going to iron 2+. Because that's happening, I have overall a lower charge happening. I'm losing positive charge. I know there's still positive stuff here, but it's going from +3 to +2. To help balance that, I'm going to get potassium to come out of the salt bridge and help balance out the charges here. Two things I haven't mentioned that usually go in this diagram. My electrons go through the wire. I didn't put electrons in these reactions. Plus an electron here, plus 2 electrons here. Sorry, I forgot to put the electrons in the half reactions. Since my electrons are being generated at the anode, my electrons are going to go from anode to cathode. So electrons are going to go from my anode to my cathode. They're being generated at the anode where my oxidation is. So oxidation is losing the electrons. My reduction needs those electrons to make the reduction happen. So the electrons are going to move from the anode to the cathode. Last but not least, because it's a galvanic cell, which we did demonstrate in a couple of ways, every time we calculated the E cell standard for this, it's been positive. Since this is a positive E cell standard, this is a galvanic cell or a voltaic cell. So therefore, I also know that my anode here is going to be negative and my cathode here is going to be positive. Now, something that I've run out of time for, but something that I will mention. So we are doing electrolytic cells, and I actually have accidentally avoided that in this entire exam review. But something that I would recommend, so we'll talk about them for 4 minutes. So an electrolytic cell, to draw a bigger beaker, is non-spontaneous. Since it's non-spontaneous, we actually have to apply a current. We have to apply electricity to this. So typically when you see an electrolytic cell, it still is going to have an anode and still going to have a cathode. And it's still going to have a wire, but they usually put a battery in this thing because they're trying to demonstrate that you're going to apply a current. And for this exam, we're only going to do molten electrolytic cells for exam 4. We'll do aqueous ones for the final. Now, I got 3 minutes. I can totally do that. I already wrote this one out too. So this is going to be molten magnesium chloride, bromide. That's what I wrote out already. So what I have is, because I'm given magnesium bromide, that means I know I can split my magnesium bromide. We haven't used periodic table yet. Here's magnesium. It's in the alkali earth metals. There's bromide. It's a halogen. So because I know all of that, I know that I'm starting with magnesium 2+ and I'm starting with bromide minus. So that's just because I'm Br2. It's because I'm breaking this up into magnesium 2+ and to Br minus. So that's how I know what I'm starting with, because I can break apart a salt. Then from there, I can actually use that standard reduction potential table to know what happens next. There it is. I know it's very small, but my magnesium is over here. So magnesium 2+ plus 2 electrons goes to magnesium solid. So this is going to gain 2 electrons and go to magnesium solid. And then my other reaction is bromide minus. Finding this is a little bit trickier because it's on the other side. But this is then going to be 2 Br minus is going to give off 2 electrons and be bromine as a liquid too, as a liquid. So that actually tells me which one's oxidized and which one's reduced. So my magnesium's getting reduced and my bromide's getting oxidized because of what I had to start with. Now, here's the weird part. The site of reduction in an electrolytic cell is still the cathode. So this is getting reduced. This is still the cathode, because the cathode by definition is the site of reduction, always, no matter what. The bromine here is getting oxidized, this is going to be happening at the anode because the anode is a site of oxidation, always, no matter what. So I could go ahead and say that I am basically coating, let's put the cathode over here. So my cathode's over here. This is where reduction is happening. So I'm getting magnesium 2+ to basically turn into magnesium solid, which means I'm getting a coat or a layer of magnesium on this electrode. And then my anode is generating bromine as a liquid at my anode because that's where it's being oxidized, because an anode is the site of oxidation always, no matter what. And the electrons are actually still moving from anode to cathode because I still need the electrons that are being generated from the oxidation reaction to be used in the reduction reaction. That's still happening. But the charges are different. My cathode is negative in an electrolytic cell. My anode is positive in the electrolytic cell. You can think about this in one of two ways. Either one, your electrons are now moving to the negative thing. They don't want to do that, by the way. This is a non-spontaneous cell. Those electrons are negative and they're heading to the negative electrode. They don't like that. Non-spontaneous, they are being forced to do that. That's why there's a battery there. So the battery is forcing the electrons to go to the cathode, which is negative. Electrons don't want to do that. They are negative. They don't want to. They're being forced by the battery. The other way to think about this is, and this is more of the actual truth, but I understand on the exam some issues want the easier way to remember stuff. Those charges actually come from which is more likely to happen. So they're named, so the charges are actually coming from the standard reduction potentials. So when you look at the table, which I don't think I made the table small enough to do this, but you can kind of see when I scrolled, or I could zoom. So my jiggy jaggy lines. So my bromine reaction's actually here, and my magnesium reaction's down here. My bromine is actually should have a positive reduction potential because my or has a more positive reduction potential because it's closer to the top of the table. The magnesium should actually have a lower reduction potential because it's closer to the bottom of the table. And what we do see then when we look at the diagram we made is that my bromine has the more positive reduction potential and my magnesium has the more negative reduction potential. And that's actually where those signs come from, is their reduction potentials. But they're being forced because it's an electrolytic reaction. It is 6:03. I went over. I was bad. I try really hard to respect the living learning community folks' time, and I went over by 3 minutes. So we're done. They will let me know about any extra additional questions. I've already promised to do 2 exam questions that I will do in the follow-up video. I just like those, and as previous, if there are other questions in the chat, I'm going to do the chat questions first, and I'll do the exam questions last in the follow-up video. But that's it for time.